Okay, so we've looked at kinematics in Cartesian coordinates and NTB coordinates. Here's another coordinate system. It is the r hat, theta hat, k hat coordinate system. So this is the same k of Cartesian coordinates. It's the z-axis, and it's pointing outwards up towards us. I guess this is really still the x and still the y-axis, but in this coordinate system, from the origin, we're going to measure the distance r, and from the positive x-axis, we're going to measure the angle theta. And if there was anything coming in and out of the page, that would be along the z-axis. So this coordinate system is fixed. Unlike the NTB coordinates, here's the tangential direction and here's the normal direction, which move as the particle travels along the curved path. The origin here is always fixed. Now, for our unit vectors in this coordinate system, we're going to have, if this is the radial direction, then r hat points like this in the direction of increasing r. The direction of increasing theta will be anti-clockwise in this case, so theta hat is perpendicular to r hat in the direction of increasing theta. Now, there's another angle of interest here sometimes that we need to do component analysis. It's the the radial tangential angle, and it's sometimes called or labeled as a psi. So it's from the radial to the tangential direction, and we'll often need that to do component analysis when we're doing dynamics. Okay, but let's focus on kinematics now. So first, let's start off by stating the position in cylindrical coordinates. Well, you're a distance r away from the origin in the r hat direction, and there's no theta hat component. That looks a little odd, but remember, r hat varies. It's non-constant, and you can see that if you, to get to this point, you're just going in the r hat direction, and you're going a distance r. Let's see what velocity looks like in cylindrical coordinates. There's the distance, and there's the direction one more time. So for velocity, we're just going to differentiate that. Now we have to do the product rule. So we'll differentiate r first, and that'll be in the r hat direction, and then we'll leave r constant, and we have to do the time derivative of the r hat direction. So what's the rate of change of that? So let's look at a picture. So here the particle was at a certain point along the curved path. This is a little bit later. It's now over here. And you can see that the r hat unit vector is changed a little bit. There's been a tiny little bit of change in its direction. And it's going to be that the change in direction is going to be related to the little bit of angular displacement that's occurred in this tiny time interval dt. Now, what we want to find is we want to find the rate of change of that r hat vector. Now, we'll appeal to calculus here, and the rate of change of r hat is the limit of delta r over delta t as delta t goes to 0. Now, what's delta r hat? Well, that means a subtraction, so we're going to do r hat final minus r hat initial, and then we'll divide by time, and then we'll take the limit as that goes to 0. Here, let's just try moving that over a little bit because I forgot to write the limit. And I should set a good example and do that. So it's the limit as delta t goes to 0 of this. So I have to do this vector subtraction. Well, if you take r hat final and then subtract r hat initial by adding the opposite of this one, so if we turn that one around, then you end up with a resultant that's going to point in this direction. So this is delta r hat. That's the vector subtraction of those two. So you'll do r hat final, and then you'll add this one head to tail, and then your resultant will be like that. But I'm just going to translate my resultant over here. Now notice that that is in the theta hat direction. So r hat final minus r hat, this vector, which is delta r hat. First of all, it's in the theta hat direction. So we're subtracting two vectors, so we're going to get a third vector, and now we know what its direction is. We can state that it is in the theta hat direction. And then how long is it? Well, this triangle is very small. This angle is very small, and so we can sort of imagine this as being like the little arc of a circle. And because arc length s is r theta, this is going to be the length of that vector delta r hat. The radius is just this length here. That's going to be the length of our r hat vector times the angle, which is the tiny little delta theta between those two. Now, the length of r hat is just 1 because it's a unit vector. So we've got the length of delta r hat is d theta, and we know it's in the theta hat direction. So this vector then is going to have a magnitude delta theta. Sorry, that should be a delta theta. There we go. A delta theta, 1 times delta theta. So the magnitude of the vector is delta theta, and it's in the theta hat direction. Now, in the limit of very, very small delta t's, this just approaches the derivative. So it's d theta dt in the theta hat direction. Now, that's actually what I set out to prove, that the d dt of r hat has magnitude d theta dt, and it's in the theta hat direction. You could also, in a similar way, prove this using the same sort of definition of derivative, do the vector subtraction, use the arc length formula, and appeal to take the limit and change d theta dt and delta theta over delta t into d theta dt. So let's use that now and go back to our velocity calculation. Recall that we had written it, we had gotten it this far, dr dt r hat, and then we had r times dr hat dt. Now we can say that dr hat dt is this. It's d theta dt in the theta hat direction. Now, to clean that up a little bit, we'll introduce dot notation. So a dot on top of r indicates time derivative. So here's the time derivative of r. So we've got r dot in the radial direction. And then here you've got the time derivative of theta. That'll be theta dot in the theta hat direction. So if you know what your radius and angle are as functions of time, then you could state your velocity vector. Now, if we visualize that then, that second term, this r theta dot in the theta hat direction, because d theta dt is omega, then this is just taking us back to some elementary physics we knew before. The linear velocity of the edge of the circle is given by r omega, where omega is the time rate of change of the angle theta. So that part we've seen before. But this term here is a new one. And this is going to happen when we have a changing radius. So say we're not moving in a circle, say perhaps we're moving along an elliptical path like a planet would as it travels around the sun. Now you're going to have a radial component of velocity, which is r dot in the radial direction, and you're going to have this theta component, which is r theta dot in that theta hat direction. And so your resultant velocity is going to be the tip to tail sum of those two. Remember that that is purely in the tangent direction, right? The resultant velocity defines the tangent direction, and there's no normal component. So this was in NTB coordinates. This is now in these new cylindrical coordinates. Now, we can repeat that same process that we just did of doing a derivative to find out what the acceleration looks like in cylindrical coordinates. So we're going to differentiate velocity. Well, velocity was r dot r hat plus r theta dot theta hat, and now we need to do the time derivative of that. So here it is in ddt notation, here it is in dot notation. So we're again going to have to do the product rule here. So first we'll differentiate r dot and get r double dot. Then we'll leave r dot constant, and we'll have to do the time derivative of r hat. Now here we'll have to do the triple product rule, which means just time differentiate them one at a time and leave the other two constant. So we'll time differentiate r first and leave the other two constant. We'll leave r constant and time differentiate theta. And then we'll leave r and theta dot constant and time differentiate theta hat. Well, the ddt of r hat we saw earlier was theta dot theta hat, And we'll now use the fact that the rate of change of the theta hat direction is, so this term here is going to be, need a bit more room, r theta dot, and then this is going to be times minus theta dot in the r hat direction. So now we'll gather all the radial terms, and you see we've got r double dot minus r theta dot squared. So that is the radial acceleration. And then we've got, in the angular direction, we've got r theta double dot, and then we've got two r dot theta dot terms. So that's the acceleration in cylindrical coordinates. Now, we've seen many of those terms before in our previous physics course because theta double dot is the angular acceleration alpha. So we've seen that what's happened there? We've seen that r theta double dot term before, and the r theta dot squared in the negative radial direction, well, that's just v squared over r. So this was, it was r theta dot squared in the negative radial or inwards direction. So we've seen those two terms before. But there's a couple of other ones now. We have one related to an acceleration along the radial direction, and then we've got this other angular term, which is 2r dot theta dot. That turns out to be related to something known as the Coriolis force and the Coriolis effect. So, to summarize then, in cylindrical coordinates, this is how you find the velocity and this is how you find the acceleration. A reminder with what we've done in previous physics courses, what theta dot is and what theta double dot is. So let's just do a simple example here. Let's have an object that's moving anti-clockwise. So I'm going to have it actually move this way. Okay, yeah, the reason I want it anti-clockwise here is just that that's going to be moving then in the positive angular direction, in the direction of increasing theta. So if it's going at 6 meters per second, that's linear velocity of 6. What's happened there? Come on, you. Oh, there we go. So theta dot will be v over r. That'll be 6 meters per second divided by 10 meters. So that is 0.6 rads per second. Now, clearly, the derivative of that will be 0. And the radius is just a constant, so there's no time derivatives there. So we can very quickly state the velocity. There's going to be no radial component, and then the tangent component will just be 10 times 0.6, which is just 6 in the theta hat direction, which is, of course, what we said it was at the beginning. That's what we were given. Now, for the acceleration, we're going to have, this is going to be 0, then this is going to be 10 times 0.6 squared. So 0.6 squared is 0.36 times 10 is 3.6 radially. And then theta double dot 0, and this is just all 0. So it looks like that. So overall, it is minus 3.6 inwards, and then it's nothing in the angular direction. But of course, this is just v squared over r. So if you took the velocity of 6, you squared it to get 36, you divide by 10, you get 3.6 meters per second squared towards the center of the circle. So that really is the centripetal term. Okay, so that's the simplest example you could possibly do. So now let's add in acceleration. So this object is going to start off at rest, and it's going to speed up to 6 rads per second in 4 seconds. So you're going to get now an angular acceleration, alpha, of 1.5 rads per second squared. Now that means for theta dot, so now we can say that our final angular velocity, which is theta dot, of course, is our initial plus alpha times t. And then we could integrate again to find theta, but it's not really necessary. Okay, so the radius is again constant, so the derivatives will just be 0. Okay, so now let's state the velocity here. So again, there's going to be nothing radially, and then it's going to be r theta dot, which is 5 times 1.5 t. That's going to be 7.5 t in the angular direction. So it goes faster and faster and faster with respect to time. That makes sense. Next, let's state the acceleration. This is also going to be time dependent. And then this is the v squared over r term. This term is 0, but here we've got a 5 times 1.5. So simplifying that a little bit, we get 11.25 t squared inwards, and then we get 7.5 in the theta hat direction. Now that 7.5 is r times alpha, right? So that angular A is r alpha, and alpha being 1.5 and the radius being 5, that makes perfect sense. So that's consistent with what we would have done before in elementary physics. All right, so a couple of problems here in cylindrical coordinates. And here we're given the radius and angle as functions of time. So first let's graph them. At time 0, this is just 2. So we are, and then the angle is 0. So if this is the x and the y axis, then this defines theta 0. So we start off 2 units out here on the x-axis. At point 1, this becomes 2.4, so the radius increases. We're up to half a radian now, which is about 30 degrees. So along that 30-degree angle, you go 1, 2.5 units. Then at point 2, that's 2.8 by the time we reach a radian, which is about 60 degrees. So we're now almost 3 units away from the origin. And then when we reach 1.5 radians, which is about pi over 2, we're now a little bit more than 3 units away from the origin. So this is a sketch of the parametric curve. So we see that the radius is increasing, so we expect a radial velocity in this case. The actual calculation of that is quite simple. If you do a time derivative of this, you get 4. If you do a time derivative of that, you get 0. Here we have constant angular speed because d theta dt is 0 and theta double dot 0. So we have a radial velocity component. It's a constant radial velocity. And then in the theta direction, it's r theta dot for the velocity. So that is time dependent. It's 4t plus 2 times 5 theta dot. So those are the two components of velocity, the radial velocity and then the angular or theta velocity. For the acceleration components, it's r theta double dot minus r theta dot squared, and then it's plus r theta double dot plus 2 r dot theta dot. Now theta double dot is 0, so that term just disappears. This time though we do have an angular term because of the r dot. It's 4, theta dot is 5. So there's our angular acceleration. Now in the radial direction, r double dot 0, but we certainly have a term here, r theta dot squared. Theta dot's 5, so theta dot squared is 25 in the radial direction. So this is also time dependent. It's in the negative r hat direction, which will be inwards, and then this is 40 in the angular direction. Now, if we were to include the z-coordinate, it's very easy because the z-coordinate is just a Cartesian coordinate. Here we've got all 3 functions increasing. So at time 0, it's 2, 2.03, 2.06. Okay, then for the z function, it also increases with time. Starts off at 0, that's in the xy plane, and then it's 0.1 and 0.2. Oops. Now for the theta function, we start off at an angle 0, so we start off here on the x-axis 2 units away, and we're down, because the z-coordinate's 0, we're down on the xy plane. Then at time 1, it's 0.43, so that's, you know, that's about 24 degrees or so, so it's about heading out like that. Now the radius is still basically 2 units, and then we're up 0.1 above the xy plane. So we're kind of spiraling up here now. Then if we put in 2 seconds, that's 0.8. And that'll be 0.92, so that's almost a full radian, which is basically 60 degrees. Now we're still basically at 2 units from the origin, so r is not increasing very quickly. We're now twice as high in the z direction. So this is a spiral, right? It's rising, it's getting further from the origin as the angle sweeps it around and around and around. So that's the parametric equation for a spiral. Now in terms of the components, we just add a z dot velocity, that's the z velocity, and a z double dot acceleration. Well, in this case, there's constant z velocity and no z acceleration. And then once again, we just do the derivatives to find, that's 0.03 by the way, theta dot, we have a non-constant here, depends on time, and we have a theta double dot term 0.06. So we substitute in here for velocity, we get 0.03 radially, we have a time-dependent angular velocity, because it's r times theta dot squared. This is a little bit messy. So that's r, that's theta dot squared. And then, of course, we have the 0.1 in the k direction, the third component of velocity. Okay, then for the acceleration, there's nothing. Then again, we've got this complicated expression, r times theta dot. And so that's the radial acceleration. Okay, so now in the angular direction, it's r. There's r. Theta double dot's non-zero here. It's 0.06. And we've got plus 2 times r dot times theta dot. So that has 2 angular terms then. 2 terms in the theta hat direction. And then there's nothing in the k direction.